Hello everybody, I will start my today another live coding session. So in my today's video, I will solve this question. Most stones removed with same row or column. Okay, so in this question, I'm thinking of the 2D plane, and we place any stones at some integer coordinate point. Each coordinate point may have at most one stone. Okay, so there are any stones positioned on the coordinate, 2D plane. And there aren't any, two stones which are placed on the same position. Okay, and a stone can be removed if it shares either the same row or the same column as another stone that hasn't been removed. Okay. Given an integer array stones, given an array stones of length n, which represents the location of either stone, returns the largest possible number of stones that can be removed. Okay, so in this question, as an input, I'm given the list of list, which is stones, the location, the stones, and my task is to return the largest possible numbers of stones that can be removed and return it. Okay, so the output should be an integer. Okay, so in this question, the thing is how many stones I can remove from the board. Okay, so let's think of this example. For example, in this case, I can remove this stone first because still there is a remaining stone here in the same row, and then I can say remove this one because there is a stone which shares the same column here. So I should return 2 in this case. Okay. And one thing I have to take care is that if I remove this stone first, then I can't remove any of the stone because either of them doesn't share another stone. There isn't two pairs. There isn't a pair of stones which share the same row or column anymore. Okay, so that being said, the brute force approach should be the factorial n time complexity. So let me tell you how. So I will think the order of the stones to be removed. So I will think of any possible permutation of the index of stones, which represents the order of the stones to be removed. And then I will try to remove stone in that order for each permutation. And then if I find that it doesn't work anymore, for example, the stone in the permutation, I'm supposed to remove the stones in 2 and 4 order, but 2, 1 was possible, but then 4 is impossible because there isn't any the stone which shared with the same column or row with the stone 4. In that case, that's the end termination point of that permutation. And then I can say I could remove 2 stones in that permutation, and I will try every possible permutation in that way. Then I will return the maximum number of stones I could remove in any of the permutations. So that's the brute force approach, but I will try to optimize this. So let's think of this question as a graph question, and I will assume that each stone represents each node, and the pair of stones which share the same row or the same column, I will think that there is an edge between them. And assuming that, what I can say is, if there is an edge which is connected I should say, yeah, which is, sorry. I will think of a node, and if there is an edge from that node, then I can still remove that node, because having an edge signifies that there is another stone which has the same row or same column. Yeah. So for example, in this case, I still can remove this because it has the edge. So when I remove this, I will delete this edge between this and this, because this is now removed. Then, but still I have the edge here, so I can remove either of these two stones. So that's how it works. And when I try to do this, I can say there is a kind of island group of nodes which are connected. For example, these four nodes are connected, and these three nodes are connected, but there isn't any intersection between this graph and this graph. So I can separate them as different graphs. And that being said, I omit the proof of this, but for each group of nodes, I can remove every node except for one node. So for example, this group consists of 3 nodes, 3 stones, so I can remove 2 stones at max. And for this, because this group is composed of 4 stones, I can remove at max 4 minus 1 is 3 stones. So that's a kind of approach I can take. So this is a kind of core, something which is core of this question. And with that being said, I can use the DFS for this question. So from each node, I will do DFS to find number. Then so basically it works in this way. I will start DFS from each node. Then I will increment the return variable. This is a kind of global number counts which can be removed. So yeah, I will update this and I will return this read in the end. But one thing I have to take care is that I have to keep track of the visited node, or I should say visited set. Yeah. Otherwise, it is possible that it comes back to the previous node, or for example here in line 25 or 26, I will start the DFS, but maybe I will start the DFS from the node which is already visited as another group of nodes. So I don't want to do that. And probably one optimization I can make is that once definitely I will create the adjacency node first, probably. Yeah, I will remove the visited edges from the adjacency node every time, and in that way it can speed up. or maybe I don't have to do this. Oh, sorry, I don't have to do this actually, because once I visit the node, because I keep track of the visited nodes in the visited set, so I will never visit the same node twice, which means that I will never visit the same edge twice. So I actually don't have to do this. Okay, so that makes it. I will start my implementation. And I will build the adjacency list first. Then for each stone, and as I said, I need business set, and also I need read. Okay. Okay, so I set the DFS from this XY. Then I will take a look at every possible direction I can move from this prefix y. So I will use the adjacency list. Okay, and so here I will take a look at current x, current y, because it's not visited yet. So I will try to visit it. Then I append this. Good. And I actually don't have. Oh, no, yeah. Okay. So I will start this current count with 0. Oh no, it's okay. Sorry. I will just keep current count as it is. And here, up to the DFS from beginning XY, I will increment this. Yep, and that's it. And in the end, I will return total count. Good. Okay, so now I will implement the build adjacency list method. So how we can do this? So because for each node, each stone, I have to find the node which shares the same row or same column, because in that pair the edge exists. So what I can do is this is also nodes which shares the same row index with X. So I will do it in this way. Yep. Okay. Oh, and I actually don't have to do this. This is enough. Because if there is any other column which shares the same row X, then this row to stones becomes the empty array. So it's totally fine. Okay, yep. Oh no, wait. So in this adjacency list, okay, this should be the adjacency list of row column to list of row columns, like this. Yeah. So here it should be XY. Okay. And then I have to take care that I have to add this XY, stone XY to row to stones and column to stones. Okay. And I will return read. Yep. But one thing I have to take care is that here in line 68, so if I find 0, 0 first and then get 0, 1, so if 0, 0 is already scanned, and when I take a look at 0, 1, now this has the connection from 0, 1 to 0, 0. But I also have to add the connection between 0, 0 to 0, 1. So I will do that. So for that, yeah. Oh, and so I don't have to do this anymore. I will just append. Okay. Good. And I will do the same for column to stones. Okay, so this is it. Okay, so let me execute my code. Good, and submit my code. Okay, accepted. Great. So this is the kind of approach I can take for this question. So let me think of the complex analysis. Because basically, theoretically, what I did was the DFS from each cell, And for this main method, I can say I visit each node every single time, and from each node in line 54, I will take a look at each adjacency node every once. I can say this is exactly the number of edges. Yeah, I mean the number of adjacency nodes is number of edges from that node. So I can say in total this should be number of nodes plus number of edges. Yeah, for main method. Because let's think that in the worst case there are n squared edges between stones, because every pair of stones are connected. In that case, number of edges is n squared. So as I said, in this DFS, so the time complexity should be number of nodes plus number of edges, so it should be n squared. Also, in line 67, I have to build adjacency list. So for this one, so I can time complexity is exactly the let's see. Let's think that the adjacency list ends up in this way. The time complexity it takes in total should be the number of elements in the values. Yeah. Because how should I say? I will do some for loop in a for loop or something like that. But for every step, if I reach my 82 or 83 or 86 or 87, new element is added to the adjacency list. Yeah. So that by counting that, I can know the time complexity. Yeah. Because as I said, I don't waste the iteration step. For every iteration step in line 82, 83, 2 new elements are added to the values. And in line 86 and 87, 2 new values are appended. So that's exactly the time complexity. So, which is exactly the same as the number of connections. So it should be n squared. Yeah. So this is it. Okay. And for space complexity, what I need is visited set, which could be up to n, and also stack, which can be up to n element when all the elements are in the stack, all the coordinates are in the stack. And aside from that, in the sum method, build adjacency method, and also obviously the adjacency list, which should be n squared, because number of values, total number of elements in the values in the list are n squared, as I said, and number of keys is obviously less than n squared. Yeah, so in total it should be n squared space complexity for adjacency list. And aside from that, in line 90 and 91, I append the row to stones and row column to stones different dict, and the same for this. Number of elements in this row to stones or column to stones is for each O of n, because I will just append new element one by one to rows to stones. And even if every row is different, I have n keys and n values, but if they're duplicate in the rows, there are n values, but key should be less than n. Anyway, that space complexity should be O of n. So this should be O of n squared. Okay, so this is it. Okay, so that being said, I finished a quick wrap up on today's coding session. So in this question, I'm given the board with the stones, and my task is to remove the stones. And stones can be removed when there is another stone which shares the same row or same column with the current stone. In that case, I can remove that stone. And my task is to find the maximum number of stones I can remove and return it. Okay, and in this question, I use the DFS. So the main idea is that I will take this question as a graph question, and I will assume that each stone is each node. And if the stone, if a pair of stones shares the same row or same column, then I can say they are connected with the edge. And I can think that there are kind of groups of stones which are connected. And also there is another kind of island of stones which are connected, but there isn't connection between different groups or different islands. And I will take the graph in that way. And also I can say for each graph, each connected island of n stones, I can remove n minus 1 stones in total. So that's the idea. So with that idea, I use the DFS from each node and find the number of connected islands with DFS and increment the total count to be returned with current count minus 1. So this is it. Okay, that being said, I finished my today's coding session. Thank you so much. Bye.